Hello everyone. I hope you're doing well. Welcome to the fourth lecture in the series. In this video, we are going to be focusing on modeling with machine learning. As you may recall, in the last video, we discussed how to process data and also the thought process that goes behind the scene. For this video, we are going to be discussing the following 4 points. 1. What is a machine learning model? 2. Classification versus regression. 3. Go over a variety of machine learning models. And lastly, evaluating performance of the machine learning models discussed. Following from the previous video, we are going to use the Titanic dataset for this video as well. So without further ado, let's dive into it. It's the same usual setup. First, I will mount my drive and head over to the folder where my dataset is located. Now, I will import the required libraries and store our dataset in a pandas data frame. Next, I'll do some simple data preprocessing. I can definitely do a lot more here, but we're going to keep it simple for the purposes of this video. First, I'll drop the columns and rows with a lot of missing values. Then, I'll remove the variables like passenger ID, name, and ticket because they don't help us in predicting our Y variable, which is survived. Lastly, we'll create dummy variables for our categorical variables, sex and embarked. These dummy variables will then be added to our dataset. Whenever we work with a machine learning problem, we tend to split our data into two parts, train and test. You can't have your model learning on the entire dataset because then you will never know how it will perform with actual data. So the training set, as you may have guessed, is the set of data your model will learn from. The testing data is like a final exam for our model, helping us in evaluating its performance. Now, the question is, how do we split our current dataset into two parts? We'll simply use the train test split function from the model selection library. Before running this function on our dataset, we need to separate our input and output. The input will include everything other than the survived column, and the output will be the survived column only. Currently, our test size is set to 0.2, which means 80% of our data will be used for training and the remaining 20% will be used for testing. Feel free to change this parameter while running your code. It's set to 0.2 by convention. Shuffling is again a common practice adopted while splitting datasets. When this parameter is set to true, the rows are randomly placed into the training and testing sets. As you can see, the training set includes 569 points and the test set includes 149 points. Now, if you work out the math, you'll see the data was split using our given test size. To reduce overdependence on a particular set of variables, a good machine learning dataset should be standardized. With the help of the standard scalar class, we'll scale the data such that each column has a mean of 0 and a variance of 1. For training the scalar model, we'll only use the training set, but after being trained, we'll use the same model to standardize both the test and the training sets. To standardize a dataset, we use the transform function. Now, we have reduced the bias and created a level playing field for all the parameters involved in the prediction. Another transformation technique we use is called dimensionality reduction. One way to do this is using the PCA class from the decomposition library. For the scope of this video, I won't discuss the math that goes behind this algorithm. For now, just keep in mind that this class helps us in projecting a dataset in a higher dimensional space into a lower dimensional space. We want to visualize the dataset in a 2D space, so our principal component parameter is set to do. Then, we use this code to actually visualize our data. Okay, so let's come back to the problem at hand now. Developing a model to predict the survivors of Titanic. For doing this, we need a machine learning model. To put it into the simplest of terms, machine learning models are mathematical representations of real-world processes. There are two types of machine learning models: classification and regression. Classification algorithms are used when the output is discrete, like yes or no, true or false. Regression algorithms are used for continuous outputs, usually in the form of numbers. Here's a list of some of the mainstream classification and regression algorithms used in today's world. Pause the video and take a few seconds to think which category of algorithms will come handy in our problem. If you guessed classification, then you were right. Our output is in the form of zeros and ones, which makes it discrete. Hence, we'll use classification algorithms. Now, let's go over the classification models we are going to test for our problem. We are first going to consider a decision tree model. A decision tree model classifies the data based on a set of questions, asked in a top-down approach. When dealing with decision trees, questions are called decision nodes, and the data point is finally classified at the leaf node, also known as the terminal node. Since we aren't manually creating a decision tree, we need a system to decide the placement of decision nodes inside the tree. For that, we use the Gini impurity system. Here's the formula for calculating the Gini impurity, followed by an example. Feel free to pause the video and go over the example. A leaf node is reached when further classifying the data using more decision nodes will only lead to higher Gini impurity. Now, we'll visualize the decision tree to aid your understanding. I'm setting the max leaf nodes to 8, which means, as you may have guessed, the model can't create more than 8 leaf nodes, and will keep classifying the data till 8 or less leaf nodes are achieved. Here's our decision tree. For the root decision node, the model chose gender, as it had the lowest Gini impurity. When data was classified using the root decision node, the model again used the Gini impurity system to classify the leftover data on both sides. Finally, the model gave us 7 leaf nodes. Okay, so let's move on to the next model now. Logistic regression is much like the linear regression model. The difference is that here a straight line is used as a boundary between data points, rather than acting as a line of best fit. In logistic regression, points falling on one side of the line are classified as x, whereas points falling on the other side of the line are classified as y. To build this model, we'll import the logistic regression class from the linear selection model. Then, we'll create an instance of that class and train the model on our training set. In order to make predictions using our model, we'll use the predict function on our test set. The result is this list of zeros and ones, predicting the survivors of the Titanic. Next, we are going to look at neural networks. I'm not going to go into much detail for neural networks as you will discuss the same in your upcoming deep learning lecture. I would recommend all of you to head over to the playground link that's on your screen right now. This will help you in understanding how a change in parameters, layers, or neurons affects your final model. For building a neural network, we'll use the MLP classifier class from the neural network library. The solver is set to LBFGS, which is an algorithm used for weight optimization. Alpha, also known as the learning rate, is set to 10 raised to power minus 5. The hidden layer is set to 3, 5. This tuple represents how many nodes will exist at each hidden layer. Lastly, the random state determines the initial values of weights at each node. So, we train this model on our training set and then test its accuracy on both the training and the test sets. Naturally, it has a higher accuracy for the training set. Now, we'll discuss support vector machines. There are two types of SVMs, linear SVM and kernel SVM. A linear SVM separates data points using a linear line with maximum margin. A kernel SVM separates data points using a non-linear boundary. Here are some visualizations to aid your understanding. In this case, the linear SVM will choose H3 instead of H1 and H2 because it has the maximum margin. Sometimes we'll encounter data that is not linearly separable, much like this one. Then we'll have to use an SVM kernel. Basically, a kernel transforms a dataset into a higher dimension where it is easily separable. When these data points are mapped to a higher dimension, they become linearly separable. Technically, all SVM models are kernel based. However, in the linear kernel, the data is not transformed at all. Now, we'll classify our Titanic dataset using SVM kernels, linear and RBF. As you can see, the testing accuracy for both the models doesn't differ by much. So, in this case, both models yield similar results. Now, it's time to visualize our results. We're going to visualize our models using this code. I think all the 5 models did a pretty decent job at classifying the training data. Now, pause for a few seconds and think which model is most suited for our dataset. Okay, I hope you were able to decide on one. Instead of estimating which model does the best job, let's mathematically analyze how our models will work with the test data. Since we have a classification model, I think using a confusion matrix for evaluation will be a good idea. A confusion matrix tells us how many labels were predicted correctly and how many weren't. It also helps in catching a bias in our classification. To visualize a confusion matrix, we'll use the plot confusion matrix function from the metrics library. So here are the results. The sum of the numbers in the bottom left corner and the top right corner will give us the total number of labels predicted incorrectly. So let's go over each model. The decision tree predicts 30 labels incorrectly. The logistic regression model beats the decision tree and predicts 26 incorrectly. The neural network predicts 33 labels incorrectly. Lastly, the linear SVM predicts 26 labels incorrectly, and the kernel SVM predicts 27 labels incorrectly. So, it seems that the linear SVM model and the logistic regression model outperforms the others. However, as you can see, the difference between the inaccuracies is not much and can be dealt with by changing a few parameters of the models. For example, removing a hidden layer from the neural network or changing the maximum leaf nodes of the decision tree.